All right, so let's start first. Before I open the application in front of you, before I open Abacus, I'm gonna be asked how to download Abacus, right? So to download it, it's very simple. You go to Google and Abacus download, okay? And you find it from here, student version. And the difference between the professional and student version is that you can process bigger files in the professional version, but for the practice here, you can just use the student version, okay? So let's get started. When you open Abacus, the first thing that you will see is this page. And we're gonna be using, we have three options to open, and we have the standard explicit model. We're gonna be using this model here. Here, if you're interested to perform CFD, do you know what it stands for? No idea. Computational fluid mechanics. So if you want to do any computational fluid mechanics, you go here. Here for electromagnetic models, I never use these actually, and you know I hate fluid mechanics. So let's get started with the explicit, the standard and explicit. And if you want like a very brief difference between the standard and the explicit, standard is usual for static analysis. Explicit is more used for dynamic models. If you have dynamic models, fracture models, dynamic fracture models, you can use the explicit ones. The standard one is based on iterations. You keep performing iteration to solve something, while the explicit one is increment based. So you take the initial stage, and then you increment it to the next stage, and so on. If you want to know more, you can just Google them and see the difference between explicit and standard models. So since we're performing static analysis here, we're gonna directly go with the standard and explicit model. Good. So when I open the program, the explicit and the standard model, you will see this. I'm not gonna tell you this is the menu bar or this is whatever thing. I'm just gonna start directly with an example. And I know other courses, they tell you like, let's model a concrete beam or a steel beam, whatever. And when you get results at the end, these results don't make sense. You get results, you know what I mean? But you don't compare them to theoretical equations or compared to real life things, okay? That's why I designed this course to be for total beginners and to make sense of the numbers at the end, okay? So the previous video that you watched, that me and Sari created, it showed you the actual deflection, and we showed you the equation that we use for theoretical results as well. So here we're gonna find the finite element analysis results, that you know that Abaqus incorporates this this method for calculations. So yeah, using Abaqus, if you go through the logical process, it's very easy. So first we're gonna do, you see the module thing here, we're gonna first start by part, then property, assembly, etc., etc. So the first thing in the part, we're gonna construct the part. I wanna construct this ruler, okay? So I go here, part, or here, it doesn't matter actually. So let's go here, create part. Here, for if I have several parts, I can manage them here, but let's just create one part now. Create part, and here I'm asked what type of problem I have, what type of modeling space I have, okay? Do I have a 3D thing? Is it a 3D? Yes, it is a 3D. So I go to 3D thing here, okay? Here, 2D planner, if I have, you know the trusses. If I have a truss, 2D truss, I can analyze it here, okay? Axisymmetric, if I have cylindrical stuff, anything, you know what I mean, axisymmetrical, I can use here. As for the type, is it deformable?
Yeah.
Yes, it deforms. So I'm gonna be using deformable type of object or type of model for this part, for the ruler part. It's not discrete rigid or analytical rigid or anything else. It's deformable, okay? For rigid thing obviously means what? It doesn't, it deform, okay? Simple. For the shape, what type of shape I want to use? Is it solid? Is it shell? Is it wire? Or is it a point? For this thing, okay, so this is very important. The difference between using, this is a big topic actually in finite element analysis. Shell element versus solid element. Shell element, from the word, it's something that is thinner, right? It sounds thin. So anything that is usually thin, a membrane or anything that is not thick, we use shell elements for it. For solid elements, something that has bigger thickness compared to the length. Usually there is like rule of thumb. I have this here thing. Where is it? They tell you if the depth, let's call this h, okay? The depth to the length the ratio between this to this, if it is less than 0.1, you see that? Which means if the length is 10 times the depth, we can use thin shell elements, okay? If it's 0.4, we can use thick shell element. If the thickness is so large, you see, when we move here, it means the thickness is large, we use solid element. However, I don't want you to always follow this. I want you to try, get the results from shell elements, and then also try solid elements. Good? Like compare the results, and if you can compare them to the theoretical values and see which one makes more sense. So yeah. Anyways, so let's use here, if we divide 15, it was 15 we said, 15 centimeter over 0.07 centimeter, right? It was 0.7 millimeter, which means 0.07 centimeter, right? So when we divide them, it's going to be much more, less than 0.1 by much more, right? So we can use thin elements or shell elements here. And the thing is, the shell element is not planar. We're going to extrude it. So I'm going to draw this part. I'm just going to draw this, just a line, a small line like this. And I'm going to extrude it. How much? 150 millimeter, okay? So I'm going to use here extrusion, okay? And the approximate size. So here, it's not necessary to know what is this. Like regardless of what value here you put here, you're going to get the same results. When they draw grids, they're going to draw grids. So they tell you what is the approximate size of your model. How much? I'm going to draw how much here? 26? 26, how much I said? It's 26 millimeter. So let's put it double. Let's say double. Okay, let's put it 50, for example. Good. And we click continue. Good. Anyways, this is a grid. Abaqus draws this grid, and we're gonna start drawing just this part. I said just this part. So I go here. See the line here? Create lines. I create line. Okay. By the way, people might ask you, can you use the same commands that you use in AutoCAD? The answer is no, they are not the same commands. You might find similar commands here, but it's not the same. It's not the same company, okay, that made Abaqus. So we can click here on the point. I'm gonna start from the origin, okay. You can actually type on the keyboard. Say, you see here, 0. You can either click on the origin, or you can type it here, 0. You see, they tell you X and then separated by comma. 0, 0. Enter. Nice. Good. And if you want to enter the other coordinate, it's gonna be what? I'm gonna draw it like that, okay? I'm gonna draw it like that, horizontal. You can draw it like that as well, it doesn't matter, but I'm gonna draw it like that, okay? I'm gonna draw 26, 0, right? Good. See? It's here. It's out of the grid, but it doesn't matter, okay? The grid is just for visual things, okay? It doesn't matter for analysis stuff. And I'm gonna click escape, okay? Now, you tell me how did I input them without actually specifying units, right? I didn't specify units. You saw that. I just put 26. So this is the interesting and sometimes annoying thing about Abaqus. Abaqus doesn't have units inside of it. So you need to maintain that all of your units are consistent with each other. What does it mean? I have this table to make it easier for you. For example, if I'm using length, I can use millimeter. But if I want to specify in my mind, I'm going to say like, okay, here I'm going to use in this model, I'm going to use millimeter for length. And if I decide that I'm going to use a Newton for force, then I am forcing myself to use, for example, for stress what?
Pascal.
A Newton per millimeter square. You see that? Or it's the same thing as megapascal, no? Is it? It is the same thing as megapascal, yes? Yes. You see the idea? So when you choose the length and the force, you're forcing yourself to use a stress of this unit. Good? Okay, clear. Again, Abaqus doesn't have unit inside of it, so you need to maintain consistent units on all of the parts and all of the modeling procedure that you're doing, so that when you get the results, it's going to be in terms of whatever unit you used. Okay, good? Let's go back here. Again, I'm gonna click escape. Okay, another question you might ask me. I just drew this line, right? I didn't draw the thickness, right? So I drew the line without actually drawing the thickness. In the next module, the property module, we're gonna put the thickness. the thickness of the this ruler. Okay, again, we're drawing shell. In shell, we don't actually we don't draw it as a solid. If I want to draw it as a solid, if I'm in the solid module, I would draw all of it. Okay, I would draw a rectangle. Okay, the whole thing here. But in a shell element, I just assign a thickness to whatever I drew. You see the difference? For example, when you draw a beam, like you know it from static analysis. If I'm drawing a beam simply supported beam. When you draw the beam, how do you draw the beam? You just draw it as a line, right? You don't actually draw it as a cross section. You don't draw the cross section. And when you analyze it, you say, okay, what's the modulus of elasticity of this beam? What's the moment of inertia of this beam? But you don't actually draw the beam, the cross section. You just assign a thickness to it and you assign a moment of inertia to it, but without actually drawing it. So the same thing is followed here. You just draw the thing and you assign a thickness to it. When I'm done drawing this thing, I just drew this thing, that's it. Okay, I click done. And they tell me how much you want to have a depth. How much you want to what? Extrude it. Okay, what's the extrusion depth of it? How much it was, we said? Here, from here, it's 150 centimeter or 150 millimeter. I cannot put 15. I cannot put 15 and say centimeter. No, it doesn't work. Okay, I need to put what? 150. They tell me here, do you want a twist? Do you want a draft? Do you want to twist like that? Okay, you know what I mean? Do you want it to be like that? No, I don't want that. It's straight. I'm assuming it's straight, even though it's a little bit crooked. But yeah, I'm assuming it's straight and I click on OK. Good? Nice. Okay? So yeah, we're done with the part module. The next part is what? The property module. Good? Now I went to the property module. I'm here now. And when you're done with something, okay, I drew this thing. I told Abaqus, these are the dimensions. But what else I need to tell Abaqus? I need to tell Abaqus what?
How thick it is?
How thick it is, yes. What else? I need to tell it that this is a steel ruler. This is not plastic. This is stainless steel. So I need to define material. Okay, so to define material, again, here there is, if I have several material, I can manage them here, okay? But I have just one material here, so I create material here, okay? Either I create material here, click here, or I go to the manager, the material manager here, and create the same thing, okay? It doesn't matter. So I create material here. What do you want to name it? Let's name it Hamid Stainless Steel. Good? Good. Okay, so they tell me here, description, if you want to add anything to yourself for later to see it, it doesn't matter. But here, okay, we named the material. It doesn't matter what you name it. Just naming it, Abaqus will not know that this is stainless steel. You see the thing, okay? So naming is just naming. Here we want to specify the properties of this material. You can see this stuff, you can play with them. Okay, for general, we have density, you have whatever thing here, whatever properties you want to assign. If you have density, you use density if you want to assign later self-weight, for example. I'm assuming, because look here. When I hold the ruler like that, does it deflect on its self-weight? No. You see that? It's very straight. So I'm saying that the self-weight doesn't actually deflect the ruler much. It doesn't affect it. Okay, the only external thing, the oranges that we added, that's the only thing that actually makes it deflect. So I'm gonna ignore the density here, but I'm gonna go to elasticity and mechanical property, and I go to where? Elastic. I'm assuming that this stainless steel is elastic. Okay, now the modulus of elasticity, Young's modulus. It's, you know what's Young's modulus, yeah? Young's modulus, okay, let's go stainless steel stress strain curve, okay? This is a typical curve. What's the Young's modulus? You see this elastic line here, right? You see it here? The slope of this line, after you do the experiment, stress and strain, the slope of this line is the modulus of elasticity. And this is the one that we're gonna use. Now, how much is the modulus of elasticity of steel? It's around, it varies from, you can just, anything, any material that you want to use, you just Google it, search for it, search for the material property. Steel modulus of elasticity. We have several types of steel. We have stainless steel, we have structural steel, we have mild steel. So you see which one you're using. Okay, but check the reference that it's a valid reference, okay, please. But just for the sake of the example here, 200 gigapascal, I saw another website showing that it varies from 193 gigapascal to 200 gigapascal. So you get an idea about the range of the variation here. So I'm gonna say it's 193 gigapascal. Now I cannot plug 193. You know why? Because the units. Okay, I need to change it to make it consistent with the previous unit. So let's see. 193 gigapascal is 193 times 10 to power 9 pascal, because giga means 10 to power 9. E, what is E? Not everyone knows that. E just means 10 to power something, okay? So E9, it just means 10 to power 9. So E9 pascal, okay? 193 E9 Newton, pascal is a Newton per meter square, and it means this is 193. If I convert meter square in the denominator to millimeter, I multiply 10 to power 6, okay? E9, and we have E6 in the denominator. We are left with 193 E3 Newton per millimeter square. Good. The Poisson's ratio is the ratio of, I'm not sure if I can find something here nice. A Poisson's ratio. Poisson's ratio is the ratio of the lateral. You can read about Poisson's ratio here. Is the ratio of the lateral. Okay, when do you have anything to use? Poisson's ratio, it's not important to put any number here. You can put it as 0 here, but even though the stainless steel has a Poisson ratio of 0.3, but I'm gonna just tell you, I give you an idea about Poisson's ratio. So Sarah, if we have this not rubber thing, this is a cloth thing. Can you hold it like that from here? When I pull it like that, can you see? When I pull it like that, I'm pulling it in this direction, right? This direction. But when I pull it, it's gonna get here what? Thinner. So when I pull it in this longitudinal direction, it's gonna get thinner in the middle or laterally. So the ratio of the lateral strain over the longitudinal strain is called the Poisson's ratio, okay? So first, if a material is elongates without any thinning here or without any necking here, the Poisson's ratio is how much? 0. There is nothing, okay? So yeah, this is the idea of Poisson's ratio. You can read more about it, but we're gonna put it as 0.3. So again, 193 here, 0, 0, 0, E3 we said. Actually, you can type just E3, by the way. E3, it works. And Poisson's ratio 0.3. Good? Good. Any questions?
No.
Good? Clear?
Yeah.
Good. Okay, so I'm gonna put okay. Nice. Now I created a material, but I need also now to create a section. Okay? A section is telling Abaqus how thick this is. Good. So I create a section here. The same thing. Section manager or create section. You got it? I go here. What are you gonna call it? Ruler section. Good. Let's call it like that. Good. Is it solid? No, we said it's shell. I'm gonna define a shell here. Is it homogeneous, the section? Yes, it is. I'm assuming it's a homogeneous section here. Continue. And they tell you what's the thickness here, the value. What's the thickness of the ruler here? We said how much? How much it was, we said? 0.7 millimeter. Okay, so I just input it here. Very easy, right? Very easy. Okay, here if I want to change the property, make it not uniform. If you want to change anything here, you can do it here. Okay, and I click on OK. And again, here before that, material, if I have several materials, I choose which material I'm gonna use, okay? But here I just have one material, so I'm gonna use Hamid stainless steel. Good, done. Now, I need to assign this material, this section to what? To this thing, right? So I go to assign, and they tell me, what do you wanna assign? Here, by the way, they tell me, do you wanna create a set? Creating a set is, when I want to, for example, at the results, at the end, if I want to measure deflection, when I click on, I want to measure deflection of something, they tell me, what do you want to measure deflection of what? I can just tell them, I want to measure the deflection of set 1. You see it? I click set 1. But I don't want that. I will tell you. I will just choose which exact node I want to measure. Typically, if I'm doing deflection like that, I want the deflection of this, of any node here, anything here, okay? So I don't want to create any set, okay? So done. Here, and they tell me, sorry, I go here, select again here, I select the section that I want to assign the material to, or the section to. I don't want to create any set. I click done, and they tell me what material, what section you want to use. Ruler section, I just have one. If you have several, you can choose whichever one you want. Now the definition, they tell you where you want to assign it. Do you want to assign the thickness to here to extrude it in the middle? I will show you the difference. It's good to show you the difference. I will click on OK. I'll assign it to the middle, okay? Now, can you see a thickness? It didn't show any thickness. You see that? By the way, if I want to rotate, you see this is move, panning. I click on it, and I just, with the left click here, I just click here, click and drag. Easy, right? Okay. If I want to rotate and stuff, you will see this circle. If I click inside the circle, it will rotate like that. It will move like that. But if I do outside it, it will rotate like that. Nice? Anyways, but can you see any thickness? Let's click escape. Okay, let's zoom with the wheel. I zoom like this. You see that? I zoom in or out. And let's zoom in a little bit. You don't see any thickness, right? If I want to display the thickness, I go to view, part display option. I want to display something related to parts. And I go to render shell thickness. You see it here? And how much you want to render the thickness? Do you want it to be the actual thickness to be rendered as the same thing? You get what it means, right? Like if it's 1 millimeter, it's going to be exactly here rendered 1 millimeter. Okay? But if I want to, for example, let's say 1 here, good. This is to scale. You get it? But if I want to say, I cannot see the thickness well. If you want it to be amplified or scaled up just for the sake of display, but not the sake of analysis. You see the difference, okay? I click on display. If I just want to see it in a better view, I click on, for example, 5. Okay? Here, it didn't change the thickness. It just changed how it's displayed, okay? Let's keep it 1, okay? Let's keep it 1. And I click on part, and I do it 1. Good. Now, remember where I assigned it? I assigned it to the middle. I will show you the difference between middle and outer edges. I will show you. Let's just move it here so that I show you exactly what it means. Okay, let's zoom in. Good. So let's go to the management of the assignments here. Again, here you go here, double click here, and I assign it to where? Middle section. If I want to change it, I go, for example, let's go top section. I will show you the difference. Click top section, look at the difference. You see the difference? It assigned it top, okay? Now, sometimes you don't know which one is top and which one is bottom, okay? So you can change them and see visually which one works for you. So I'm going to keep it where? Middle section. So we're done with the property module. We told Abaqus, this is a stainless steel ruler. It has these dimensions and it has these properties. So next, what do we need to do? We will go to the assembly, which means assemble the model that we have. Now, I go to the assembly module, and the assembly here doesn't make much sense. Okay, let's say, give me something that is made of several parts, for example. Give me something, I don't know. Yeah, so yeah, I have this marker. Okay, on Abaqus, for example, if I want to analyze this marker, it's made of several parts, right? I constructed now just the ruler because the whole model just have one ruler, okay? The oranges that we had is not parts, it's just loading, okay? So here, I can draw one part, and then I draw the other part in Abaqus, and then in the assembly, I tell Abaqus how exactly they are assembled together. Nice, okay? But here, how many parts I have? Just one part. So I just go here, create an assembly here, and they create the instance of the assembly. Okay, and I'm gonna create just one part. Done. I just have this part. Done. I don't have anything else. So yeah, but if you have several parts, you need to join them. Okay, so yeah, in the next section, we're gonna tell Abaqus that we have this ruler in equilibrium when we attached it to the table, but we're gonna tell Abaqus what type of analysis we're doing exactly, because you know there are several types of analysis. So we will cover that in the next module. The next step is to go to the step module, okay? And I go here. Good. So initially, okay, I need you to look at it in a different way than what we used to during structure analysis courses. So I have the ruler. It was attached. Did anyone touch it first? No. It was just like that, okay? Held by the table. Nothing, okay? Nothing else applied to it. And then later, I applied the load to it. So the initial stage, there was nothing, right? Just the boundary condition here. Just I'm gonna tell Abaqus that someone was holding, which is the table, the someone holding the ruler from here, okay? And in the next stage, we came and then we put the oranges here, okay? So how many stages do we have? Two stages, yes. So I'm gonna go here. The initial stage, it's always by default there, okay? I'm gonna create a new stage here, a new step. And they tell me here it gets interesting, okay? So I'm not gonna go to advanced stuff. I'm gonna do just a static general analysis, okay? We call it static. You're gonna tell me, okay, but I'm applying the load like that. Why it's static? Why it's static even though I'm applying a load? Because I'm applying the load in a very slow way. Okay, if I upload like that very fast, it becomes dynamic analysis. Okay, we're not interested in that. We're gonna just perform static general analysis. You can perform buckling analysis. You know buckling. If I'm loading it like that, it's not a regular deflection problem. It's a buckling problem. Buckling is not here. It's not in general. It's linear perturbation and you go to buckle. This is more advanced. We're gonna do just general analysis. By the way, if you have any question about this, or if you have more information you want to know, you have a whole documentation about Abaqus. You can go Abaqus manual, easy, right? And you find the documentation about Abaqus. If you want to have any problem with here, you have also examples, anything you need, okay? But here it's just simple. Let's keep it simple. So I go general and static, continue, done, okay? And I'm here, if you have any nonlinear or nonlinear effect of general, like if I have, usually in static analysis, we assume that the deflections are small. If you go back to the theory, Euler-Bernoulli theory, how it was derived, okay? The whole differential equation that governs the deflection. If we have large displacement, this is another type of analysis. But here, I'm assuming everything is fine. I'm assuming the deflection is small, even though it was large. Right? Even though it's large compared to it was like 3 centimeter. 4 centimeter. 4 centimeter out of 15 centimeter is large. But I'm assuming to keep it simple, I'm assuming we don't have any non-linear effects here, okay? Let's click yes, okay? And now we have initial step and the step 1, okay? Where we apply the load, okay? So close this. Next, we're gonna talk about interaction. Good. So in the interaction module here, it might not seem very obvious, but I'm gonna use the interaction thing here to avoid something called stress concentration, okay? So by the way, when I applied the load like that, it deformed. Did my finger puncture the ruler? No, we don't have the problem here, okay? But if I'm using something else, let's say I have a paper. Can you hold it like that, Sarah? Up like that? Yeah, from here and here, okay? If I have a paper and I bring a tweezer, okay, a very pointy tweezer, and I put it like that. If I'm interested in Abaqus, for example, to model just the global deflection, look with my finger, it's gonna deflect globally, all of it, okay? Globally like that. But I have a tweezer, if I'm gonna deflect it, it's gonna puncture it, okay? So now it looks obvious why I'm doing that, okay? So in Abaqus, we might have local concentration problem, or stress concentration problem. So to avoid that, I'm gonna tell Abaqus, for example, to link the deflection of this point here with the deflection of all of the points around it. So that not only that point is carrying all of the load, but the load is distributed to all of the points. Easy? Easy concept. Good. So I'm gonna go here. I'm gonna say that all of the deflection, like I'm putting the load here, right? So I'm gonna put the point, gonna link all of the deflection of all of the points along this width to a point in the middle, okay? Because I'm gonna apply the load here in the middle, okay? So I'm gonna define a point. I'm just gonna define a point first, okay? Called a reference point, okay? I go here, create reference point to link it to other points, okay? I click here and they tell me, where do you wanna put the reference point? I wanna put it here, okay? In the middle. Good, done, escape, good? Now, I wanna tie this whole part, this whole edge to this reference point. Good. So I go here, coupling. Okay. I go here, create constraint. I want to constrain this edge to this point. I go here and I go to coupling. I want to use coupling. If you want to interested on these other stuff, you can go to the manual and read more about them if you need them. Okay. So let's go to coupling and continue. And I'm going to create, they tell me which point you want to link the other stuff to it. So I'm gonna use this point, reference point that I just created, okay? And I click this point, okay, and done. And they tell me what do you want to link this point to, okay? So I'm gonna link it to what? Not to a surface, I'm gonna link it to a node region, which is what? This edge and this edge, okay? This whole edge, okay? So click on it and done. And they tell me what type of links or constraint you want to create. Let's call it structure because we're doing structure analysis, it's structural modeling here. So structure distributing, which means U1, what does U1 mean? U means displacement. 1 means in the x-axis here, okay? You can use different type of coordinate. You can add coordinate system here. You can do whatever you want. But just for the default options here, 1 means in the x-axis. U means displacement. So I'm linking the deformation of, it's like that, okay? So I'm linking the deformation of this point, of this whole edge to this point in the x-axis, even though it's not moving in the x-axis here, okay? So it doesn't matter actually if you remove the U1. I'm linking their deformation, the edge deformation, this whole edge deformation in the y-axis to this point. This is what matters here. We're moving in the y direction. And I'm saying also in the z direction. Again, it's not moving much in the z direction. And the same thing, UR1 means the rotation around the x-axis. Does it matter here? Yes, that's what matters. It's deflecting, rotating around the x-axis. That's what matters here, okay? The other stuff doesn't matter, okay? But again, structure distributing, keep it default here and press OK. Done. Okay, this symbol here, the circle here, tells us that we've created this constraint, okay? We're done with the interaction. Next, we need to assign the loading. We need to apply the loading. Now we go to the loading module, okay? The first thing, now you tell me, okay, I have loading, okay? I need to assign it. What type of loading did I apply when we applied put the oranges here? It was concentrated, right? It wasn't distributed, it was concentrated, okay? But we said we want to avoid the local stress concentration problem because this is steel, this is strong, okay? We don't have the stress concentration problem. Given that it's steel and given that we're not using heavy weight for a steel to puncture, okay? Or to have stress concentration problem. So we go here, create a load. I want to apply a load, okay? They tell me what type of loading you want to apply. Let's call it oranges, okay? Because we applied oranges, okay? Where do you want to apply it? Do I want to apply it in the initial or the step one? Step one, exactly. Okay, the initial, I don't have any loading. What type of loading I want to apply? Is it a moment? Is it a pressure? Is it shell edge load? Is it whatever? Okay, there are several ways to apply it, but I'm going to use here concentrated force. Okay, and click continue. Okay, I'm not allowed to use oranges. Sometimes, by the way, the name doesn't always work. Sometimes it's because of the space that you add at the end. So let's go here like this, oranges, and continue. Good, it worked. And they tell me, where do you want to apply the load? You see here, the command always will come here. What do you want to apply here? Okay. By the way, can you see there's a script here? Abaqus can work as a programming language. You can type a script and let Abaqus run it. It's very easy, okay? I don't use that because we now have this fancy user interface, okay? But again, everything, the command that you do here, you can see it here, the command history. Anyways, we're gonna select the point that we wanna apply the concentrated load to. I'm gonna apply it to the reference point, click on it and done. Okay, so they tell me CF1, what does CF1 stands for? Concentrated force, easy, okay? So they tell me how much you wanna apply a concentrated force at, like how much is the value here that we're applying at the reference point. In the CF1 concentrated force in the X direction, in one direction. Do I have anything here? Anything in the X direction? You see the X direction? No. Do I have anything in the Y direction? Yes. Right? The force is applied in which direction? This is up, positive. This is negative. It's applied in which direction? Negative. Okay, you can flip it. Okay, it doesn't matter. But I mean, we're here following just like based on the page we're seeing here. Okay, how much is the value? Do you remember the weight that we calculated? Let's go to the weight. Is it here? I put it here. Okay, this is the weight. So yeah, here's the mass. We measured the mass of the oranges, the 3 oranges that we had, using this spring balance, right? And again, it was 0.455. There was a little bit of difference. It was once 0.456, whatever thing, just for the sake of the example. 0.455 kilograms, okay? If you're American, if you're here doing it in the States, you want to use pounds, you can use pounds, okay? But again, you need to be consistent in all of the units, again, okay? And now when we apply a force, it's a force. It's not a mass. You agree? It's a force. So I need to convert it to what?
Newton.
Yes, either pounds force, if we're talking pound thing, the US unit, or if we're talking general units, international units, we're talking about newtons, okay? How do we get the load from the mass? We multiply the mass by what? G, the gravitational acceleration, okay? 0.455 times 9.81. They tell me like, why are you using 9.81? Why something else? We're on Earth, we're the ground level here, okay? So we're using 9.81. You can use 10, you can use whatever you want, okay? Just, if you're on the moon, use something else, okay? Use a lower value. If you're, I don't know, in heavier, something heavier than Earth, you can use a higher value, okay? Lower or higher, depending on which planet you are on, okay? So anyways, it was minus 4.46 newtons, okay? So I'm gonna apply that in the minus direction, minus 4.46. Done. Okay, I don't have anything here. Okay, you can put 0 here, but Abaqus will know that it's 0 anyways. Okay, so I click on okay, but before that, this is actually something interesting I told you about. Remember, I'm applying the load like that. Okay, when the origin started going down and the ruler started going down with it, the direction of the oranges, the force that is applied here, it didn't change. You see that? Because it's gravity. It's always towards the core of the earth, okay? So it's always like that, okay? Vertical. However, there are other type of loading where it's called follow nodal rotation. Where if I'm moving like that, it was 90 degrees like that. And when I deflect like that, the loading starts deflecting like that, okay? It's called follow nodal rotation. We're not using that here, okay? So keep it simple and click okay. Good. And the nice thing about Abaqus, it will show you that the load is applied in the right direction. Okay, this is nice to see. It is actually like in the graphical interface. Okay, so we're done with the load. Now we need to apply what? We applied the load here, okay, or here. We're applying it from here, and we need to tell Abaqus that here we have what? Fixity. We have a fixed support here. Okay, so how do we do that? By the way, if you search here on all of the modules, you don't see boundary conditions, right? So boundary conditions are actually under the load module. And why is that? I told you why. When I apply a force here, can we agree that the table also applied a reaction force on the other direction? Yes. So that's why the boundary conditions are classified here. They are put in the load module. So I go to here, boundary condition, okay, create boundary condition. What type of condition I want to create, okay? I want to encaster, right? I want to encaster this whole thing. Okay, the rotation, the displacement, everything is prevented at this end. Okay, so I want to assign all fixity to all degree of freedom here from this part. Okay, and it's the category is mechanical. What type of condition? Like let's call it table. Okay, table, because this is because of the table. Okay, am I applying this in the step 1 or 1? This was in the initial because the fixity was already there. I put the ruler in the table, attached it to the table, and then I applied the load in the second step. So here I can go. By the way, you can do it either ways. You can either go to encaster here or go to displacement rotation. Okay, whichever you want, both works. Okay, so let's go to encaster here and continue. Again, I have a problem with naming. There is a space at the end. I always forget the space. So encaster and click continue. Okay, I want to go to the other direction. You can use rotation. By the way, these are the views. You see different views here from XY from the other direction, XZ, whatever thing. Okay, and here you see it in a nice view. I want to assign the fixities to this direction, right? They tell me select regions for boundary condition. I want to select this whole edge. You see it? Selected. Okay, and click done. Okay, they tell me what do you want to stop? What do you want to fix? Here, I can stop the displacement in the x direction. Remember, because they tell me displacement is equal to 0. It means I'm not allowing displacement in the x direction. UR2 Okay, UR2 is equal to 0, which means what? The rotation in the Y direction. UR3, the rotation in the Z direction, okay? So again, I want to encaster everything, fix everything, okay? So I go here to the end. U1 equal U2 equal U3 equal UR1, UR2, UR3, all of them fixed, 0. Good. Okay, so you see these stuff, you see these pins, the fixities on all directions, okay? These are not pins actually, they are not pins, they are fixity supports, okay? And we're done with the loading. Now we go to the meshing module, okay? So now we are in the meshing module, okay? We talked about finite element in the previous video, and we talked about its concept. Again, Abaqus uses finite element, but finite element is a huge topic, okay? We covered it in a very brief video, very short video, okay, in a very fun video. So here, I'm gonna just present like small points, very few points about it, okay? So again, I'm gonna start the meshing. There is something called the first part of meshing is called seeding, which tells Abaqus how I want to divide it, okay? Seeding means I want to put nodes. Let's say I want to put a node here, a node here, a node here, a node here, okay? I'm just adding nodes, okay? Let's go to seed options, okay? Click on seed part, okay? There'll be a problem, okay? Dependent part instances cannot be edited or assigned mesh attributes, okay? You might have this problem because I'm meshing the whole assembly, even though I said that this part I want to mesh it on part when you create the part. So I go here, meshing. Before I click on this, I go to here, okay? Mesh part 1, okay? So I go here, see this thing, okay? And they tell me, do you want to have a node every how much? Here, if I keep it like 15, it means every 15 millimeters, I'm gonna have a node. Easy, right? So no, I want to have a node every 1 millimeter, okay? And I click OK. You can change these options. You can change the meshing. For example, when we have stress concentration, you might want to increase the meshing or decrease the meshing depending on your analysis at that point, okay? At curves, you might increase it, decrease it. So anything that has to do with the mesh control, you control it here. But I'm gonna keep it simple and click on OK here, okay? Just 1 millimeter size, okay? You see the part? You see them? You see the nodes? So this is one, this is another one. So every 1 millimeter, we have what? We have a node. Nice. Now I go to mesh. This is where I mesh it. Okay, I click on mesh and they tell me, do you want to mesh it? Yes. Nice. So here they divided it and they assigned a mesh. They divided the whole part, as we said in the introductory video. We divided into small boxes. Okay, and this is meshing. This is discretization. Okay. Now, we talked also about what? Remember, we talked about element type. We talked about linear and quadratic. Okay, so I will tell you where we see them here. Okay, so let's select this. We click on this if we want to change the element type. Assign element type. You see it here. Okay, you click on it and they tell you what do you want to use, linear or quadratic. Okay, and whichever you want to choose. By the way, they tell you there is usually rules for that. Quadratic means you have what? More points to integrate over, more points to put into your differential or finite element analysis here, okay? Linear requires less analysis, shorter time for analysis, but quadratic is usually more accurate, okay? It depends always on the system as well, okay? So I will tell you which one to choose. I actually choose both, okay? I check the analysis using linear analysis, and then I use another analysis I perform quadratic. I use quadratic elements and I compare them to the theoretical results and see which one, the linear or the quadratic, makes sense, okay? So let's say I want to use a quadratic element here. It might take more time, but it doesn't matter, okay? It's fine here, okay? For larger models, for much larger models, you might want to change that here, okay? For quadratic models, there are two types here, quad or tri. Okay, now you might, when you start using Abaqus, you might not know all of the types of elements, but it helps you. Abaqus is helping you. They tell you quadratic, and the quad element. You go here. They tell you that this is called SR, S8R. Oh my God, what are these, right? S means shell. We're using a shell element. 8, we have 8 nodes. in each box, on each mesh, okay? R means we are using something called reduced integration, okay? Now, for big models, there is something called full integration, regular integration, and there is something called reduced integration. Reduced integration means that we're using less elements, less points, less integration points when we integrate over the whole part or the whole model. Okay, if you want to know more about this, again, you can always Google it and see if you want to use this or that. Okay, reduced integration, from its name, it will reduce your time during the computations, but it might have some problems. Okay, I don't want to cover that now, but again, reduced integration saves your time, but sometimes might cause other problems in finite element. So we're gonna use the quadratic and this element. By the way, 8 means what? We have what? 8 node doubly curved thick shell. Even though this one we said it's what? Thin, right? But you're gonna assume it's thick here, okay? It's fine. Okay, so again, you always test different elements when you're doing your research. Test different elements, compare them to theoretical results and see which one makes more sense. Okay, and again, if you want to know the element types here, you can go here, us 8 or Abaqus, okay, and you can read about them. Okay, there are lots of information online about these stuff. Okay, we have one. You see it? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 nodes. Okay. So again, you can always Google this and find free information on the internet about that if you're interested to know the difference between the elements. Okay. And we click on OK. So we're assigning quadratic elements to this part. So yeah. In the next module, we're gonna just run the analysis. So now when we go to the job module and you're going to tell me, oh my God, you skipped something here. Optimization. What is optimization? I actually never used optimization until now. Okay. But if you want to optimize a cross-sectional area, optimize the length or something else, you can put a criteria here about the optimization you want to follow, you want to use in the results, and you can do it here. I never used it, but know that you can use it here as well in Abaqus. So let's go to the job module here. Okay. Now job is a fancy way of saying, I want my results, okay? I just want something to be calculated, okay? Job, do this job for me, okay? So I go here, again, the same thing, create job or what? Job manager, okay? I go to job manager. I want to create a new job, okay? And create here, okay? I want to create the new job from where? From the model 1. This is the whole thing that we created is called model, okay? Model 1, okay? I create and continue. Done. Okay, I want a full analysis with everything. I want to keep everything in default. Okay, continue. And after that, okay, I click on submit analysis, submit it here. Sometimes if you have big file, okay, you don't want to submit and then they tell you at the end, oh my God, you have an error. Okay, you can just do that data check here before you submit it. Okay, but now it's a small model. I'm just gonna do submit. Okay, and yes. So yeah, it's gonna run now, and this is a very small model, so it's gonna run very fast, I think. So yeah, it's running here. If you have any problem, they will tell you. Sometimes it's aborted and you will die and you will feel desperate. Okay, I felt that before. So again, here, when it's successful, they will tell you it's completed. Completed doesn't mean that you did your model correctly, okay? You need to look at it and you see it's correct, okay? So you go to results, and good. We have here the results. Okay, this auto fit to make this whole thing fit into the view. Okay, a better view. It's already fit. If you want to zoom in, let me show you. If you're zoomed in by mistake, or zoomed out, you can just click here. Don't go back like this. Okay, nice, right? And we want to see the results. Okay, I want to see the deflection. I go here if I want to see the deflected shape. Nice, just like I expected, right? This is how it deflected. Remember? Like this, okay? So if you look at the side view, you're gonna see here something called deformation scale factor, okay? I got the side view from here, okay? You can get it from here or here, the same thing, but different directions. Okay, the deformation scale factor is 0.58, which means almost 0.6, okay? So what does it mean exactly, deformation scale factor? From the word, that's what it means. It's very simple, okay? It's telling you if it deformed, for example, 10 centimeter, it's gonna actually display it as, just for scaling here, how much?
6 centimeters.
6 centimeter, okay? And this is just for displacement, because if they display just how much it was deformed, it's gonna be like that, you know? Okay, so just to make it neat, Abaqus does that too. They scale down the displacement for visualization process, but it has nothing to do with the actual results. Okay, that's not where you look at the results, not the value. Okay, so we go here. Okay, if you want to see the results, you go here. Okay, I go to plot the contours here, and I see them. Let's see them on the side. Okay, let's see them not here, on the side. Okay, let's go here. Okay, at the side, and you see this is stresses. See, remember, acid stresses. This is the von Mises stresses. We're not interested in stresses here. We're just interested in deformations, okay? But it makes sense. Look at it, by the way. Look at it, okay? Here, they are telling you that we don't have much stresses here. Can you see that? Okay? Because the most stresses here come here where? At the fixed support, right? They come at the fixed support. So, yeah. And, yeah, if you want to do the deformation, remember, deformation, the symbol for deformation was what? U. So, we go to U. So yeah, we see the results here, and they tell you that the magnitude of the deformation at the fixed support is 0, right? Because it's fixed. Okay, makes sense. So we're good. Okay, and the visualization of it looks nice. Okay, which means we have good results. Okay, and we don't have any stress concentration problem because all of them have the same deformation. Okay, if we have stress concentration problem here, we might have much more displacement. Okay, so the contour would show different colors, and here it would have stress concentration, which means we have more displacement. Okay, so we don't have that problem here. Okay, the deformations are really nice. You see the contours, how they are, which means we don't have stress concentration here. Anyways, so the deformation is how much here? 2.58 E1. Don't forget the E here. Okay, sometimes you might make a mistake here. It's 25.8. What's the unit? Millimeter, because we used millimeter for all of the dimensions. We were consistent in this. Okay, now you're gonna tell me, Hamid, but this is not the same results that you got in the previous video. Yeah, okay, I wanna show you that I made a mistake actually here. Okay, I'm not sure if you paid attention to it. Where did I make a mistake? The result is showing that it's 25.8. Okay, but how much we got actually? 33, which means what? I actually made a mistake in the thickness. I used here a higher thickness. Let's go to the thickness. Let's go. We go to property. You can always change what you did before, okay? So don't worry. And you go here to the section manager. Double click on the section manager. What did I use here? Not 0.7. I used 0.077 by mistake. So keep it 0.7. I click on OK. And done. I go to the job. And you're going to tell me, is it gonna change automatically? No, you need to submit again. Okay, and we click on results again, and we go to the contours, and we find this is not the results. Okay, again, okay, this is von Mises stresses. Make sure what you're selecting here. Okay, and you go to units here, and how much is it now?
34.
Now it's almost the same results that we got. Okay, 34.39. Okay. So again, so we got the result 34.39. You're gonna tell me, okay, but what if I want the displacement at a specific point, right? What if I want the displacement? What if I want the exact? Actually, because it's the maximum here. Actually, the scale here is based on the maximum thing here. Okay. So, but if I want the displacement of say this point here or whatever point, you can remember when we created. I didn't check it. Create set. You can actually previously select a point. You can go back to the part. Okay, you can go back to the part, go to the part 1, and create a new set and say this point is called set 1. And in the result, you say I want the deflection of set 1. You get it? Okay. So again, but since I already have a reference point, which is the middle point at the free end. I'm gonna use that for calculation. Okay, it's gonna show the same results. So if I wanted to draw the displacement, I go here, create X, Y data. And I go to ODP field output. I click on continue. And I select, what do I want to display here? Displacement, right? Okay, so I go not to integration point, I go here to unique node. Okay, I want to select a specific node, a specific point. Okay, unique nodal, I click on node, and I want to measure what? Spatial displacement. Do I want to display all of the displacement, or I care about only the displacement in the y direction? Only the y direction, right? So I go here, y, because it's u2, remember? And I click plot. If I click plot, they're gonna give me an error because they tell me, okay, to which point exactly you're specifying it. Okay, so I go here, element node, and I want to pick. I can click here, double click here, and go and select which node I want to exactly draw the displacement for. Okay, but I want to click on node label and node set here. I have a reference. You see the node set. Abaqus automatically create a set for the reference points that we created. There was a reference point here, remember? So it's here. I want to select it. Okay. Highlight items in viewport, and I'm gonna select it. Look. Good. And then we're gonna click plot. Okay. And let's see the graph. They tell me from time 0 to time 1. What does it mean? It depends what you specified. I skipped that thing actually. In this step, remember this step thing? I defined loading. You can specify what time means exactly. It can mean second, it can mean anything else, okay? So it depends on the time. But they tell me, at time 0, the ruler was where? 0. It didn't deform anywhere, right? It was here. And they tell me, over time, what happened to this point? I'm talking about this point. This is not the ruler. Don't think this is the ruler, okay? This is just the displacement of this point over time, okay? When the time increased from 0 to 1, again, 0, 1, just call it anything, okay? The time here is irrelevant. But anyways, from 0 to 1, at 1, the displacement was the maximum. It was almost at what? How much here? Almost minus 35, which is actually the answer that we got here, okay? So yeah. At the end, it was like that. Now, I'm going to talk about, if we go back to the results, I used 1 millimeter mesh, right? 1 millimeter size. What happens if I change it? What happens if I go back to the mesh size and I change the seeding option? Instead of 1, I put it as 10. Remember what we said? The more mesh, the smaller the mesh, the more accurate the results, right? The closer they are to what? The theoretical solution, right? So the thing is, I want to compare and see the effect, okay, of the mesh size on the results, okay? So if I change it, and then we need to mesh again, yes, and again, I'm using quadratic element. I'm not going to change it because it's already assigned. I go to job, and I do the analysis again, run the analysis again. Okay, and I see the results, okay, and not von Mises again, don't make mistake, okay. Go to displacement. Did it change or not? Yes, it changed. It was 34.39, right? It changed to 34.36. Now what happened? The deflection decreased or increased? The deflection decreased. Remember what I said? We said the less mesh you put, the bigger the mesh, okay, which means look how big the mesh is here, okay, big sizes. It means we're stiffening the system, we'll make it more stiff, right? So that's why it's harder to bend that ruler. The ruler that is constructed in Abaqus, okay, it's harder, visualized or created in a stiffer way, okay? Now, if I do it again and use a bigger mesh size, it's gonna be more stiff, okay? Now we're comparing, this whole comparison is based, all of them, these are quadratic elements. But what if I change the type of element? What if I go here, okay, I go here, and instead of doing a quadratic element, what if I change it to what? Linear element. What do you think is gonna happen? Quadratic, which one is stiffer? Linear or quadratic? We said that. Linear, remember? Because it's approximating this thing. This is a cubic actually, you know that, from the equation. It's approximating this thing by a straight line. Straight line in terms of bending is stiffer, okay? Is stiffer than what? The quadratic element. So actually I'm expecting results that are what? Far away, yeah, stiffer than the quadratic elements, okay? So you can do that actually, you can do all of this, but I summarized the whole thing. You know how to do it. So I summarized it here at the end, okay? So For mesh size 1, this is what we used. We got how much? For quadratic element, we got 34.39. For 10 size, we got 34.36. For 50, look when I increased the mesh so much. What happened? 33.97. What happened? It's becoming stiffer. You see that? Now, let's use what? Linear elements. If I use linear element, look what happens. Here, you're going to tell me not much difference, right? It's the same thing here. For over decimal points, you will always find here the quadratic. For this case, the quadratic is smaller. You know what I mean? Or sorry, the quadratic is more. It's less stiff. Or yeah, the linear is stiffer. So, but again, this is how much we applied. Few newtons. That's why the difference is not much, okay? For bigger problems or for higher loads, you're gonna see a bigger difference here, okay? But anyways, for linear, you can see it's 34.35, and again, it's what's happening to it? It's decreasing, okay? Because it's becoming stiffer, okay? S here again, what S means, remember? Shall. 4 means what?
Nodes.
4 nodes, we're using 4 nodes, okay? And by the way, you're gonna tell me why for quadratic elements we use 8 nodes, and for linear elements we use 4. This actually goes back to the theory of finite element, okay? Because when you define the functions, the approximation functions, quadratic or linear, you need points to define the function over, okay? So for example, you know what's the equation of a straight line? Y equal ax plus b, okay? You need 2 points to define the straight line, right? What's the equation of the quadratic equation? You need more points. So that's why actually we need to use more nodes for the quadratic elements than the linear elements. Anyways, but now I'm going to compare it to the theoretical deflection. The theoretical deflection doesn't have much, it's not dependent on the mesh size, okay, because I'm just using an equation. But I put it next to them just so that we can plot them. So that when I plot them, all of them, okay. So anyways, when we look at the diagram here at the plot, the blue one is the quadratic element, okay, and the linear is the orange one, okay. The theoretical one, again, it doesn't change with the mesh size, it's the same thing. Now, I want you to notice something. When the mesh size varied from 50, by the way, this is the x-axis, is the mesh size, okay. When the mesh size, let's go in this direction, okay. This might look confusing. We're moving this, okay, in this direction. When the mesh size decreased, you see the increase here, how it's moving closer to the theoretical solution, even though there is always a difference. You see the difference here and here, okay. We will never go to the theoretical solution, okay. We move closer to it. But can you see that I'm here going there. I'm becoming more asymptotic to it, okay. This actually what we covered previously in the previous video, what we call it, convergence study, okay. And for the linear thing, the same thing, okay. It converges, okay. The slope here starts to be high, okay, because from 50 to 40, it's a big difference, okay. Not in terms of number, mesh size, or scale. I'm talking about the analysis, the finite element analysis results, okay. It's different. But when you move much smaller, the difference becomes negligible in terms of the results, okay. So that's why this is what we call convergence study, okay. And this one, if you're doing a research in finite element, you need to show your advisor or the project, the committee or whatever, that you did this analysis, so that they tell you, okay, your modeling technique is right. It's closer to the theoretical solution, okay? And by the way, you might ask me what formula I use for theoretical solution, okay? I use this formula, okay? PL cube over 3EI. L is the length of the beam. E is the modulus of elasticity. I is the moment of inertia around which axis? Around this axis, okay? I'm bending around this axis, right? So this is the axis, okay? So it's 1 over 12. B, this is B, and this is H, okay? This is H, 1 over 12 BH cubed. Actually, this should be cubed, not squared, okay? This is moment of inertia. And yeah, again, if you want any formula, you can find it again on Google, okay? Cantilever, beam, deflection, formula. Okay, you can find it here. You can derive it as well if you want, okay, but you can find it here as well, okay, here, okay. So the deflection is PL cube over 3EI, and you can find the variables defined here. I'm opening Google too much for you, I know that, right? don't trust. I'm just here. I'm opening any random pages here because I know that these results are correct. Okay, but when you get results from Google, make sure that they are correct. Okay, check them other against other authentic sources. Okay. Okay, good, clear. Okay, good. So yeah, if you have any questions, please let me know. And yeah, thanks for watching, and hope you enjoyed the course. Peace.